So we'll talk about the Fourier transform. Fourier transform is one of the most important transforms in analysis and linear algebra. And it has got lots of applications in signal processing and developing of algorithms. And we'll talk about the discrete version of the Fourier transform called the discrete Fourier transform. So let's say we have complex numbers x1, x2, xn, and we define the Fourier transform or the discrete version of it as transformation of these uh, complex numbers into another set of complex numbers. So they're all belonging to the complex numbers, and each the set is transformed to another set y1, y2, yn, and the transformation is defined in the following way. Yj is equal to 1 over square root of n summation over k xj e to the 2 pi I jk over n, where I is the complex number and k is running from 0 to n minus 1. Right? So one can think of a Fourier transform that transforms this vector. So this is a n cross 1 vector with components x1, x2, xn, n cross 1 vector, and it transforms this vector to y1, y2, yn. So one can think of a Fourier transform as a transform. So I'll label the Fourier transform of the n-dimensional Fourier transform Fn as a transformation from Cn to Cn. And one can show that Fourier transform is a linear transformation. So it is a linear transformation. Not only is it linear, but it is a unitary transform. In the sense that Fn dagger Fn is equal to Fn dagger is equal to identity. So it's a unitary transform on the space of complex number Cn. Right? And if I look at this equation, then I can write down the matrix representation of the linear transformation Fn. We'll take, and I'll just write it down. So let omega is our complex root of unity. So omega, I can label this omega n is equal to e to the 2 pi I over n. This is the nth root of unity of unity. Then the linear transformation Fn has the matrix entries omega n square, omega n to the power n minus 1, 1 omega n square, omega n to the power 4, omega n to the power n minus 2, and then 1 omega n to the n minus 1, and then this will be omega. So the matrix representation of the Fourier n-dimensional Fourier transform is given by 2 pi I over n. This is the nth root of unity. And the matrix entries Fn, the jkth entry is given by omega n jk, right? So an important thing in the theory of Fourier transform is the efficiency of the Fourier transform. Now, if I want to operate of the Fourier matrix on n cross 1 vector, then the regular Fourier transform should take order of n square basic operations. So basic operations can be right. So the n-dimensional Fourier transform takes order of n square basic operations. Now it turns out that the efficiency of the Fourier transform is an important concern, and one can do a fast version of the Fourier transform called the FFT, or the fast Fourier transform. Fast Fourier transform can be done in order of n log n operations. And this considerably speeds up the processing of signals and algorithms, right? And the reason for the speed up is that the Fourier matrix can be, or in general, the Fourier transform can be defined recursively in the following way. We have, if I have an n-dimensional Fourier matrix, and I'm assuming n for the time being to be a power of 2, then I can write this as f n over 2 f n over 2 d n over 2 f n over 2 minus d n over 2 f n over 2 times some permutation matrix. So this is some permutation matrix, right? So these are n over 2-dimensional Fourier transform, and this is a diagonal matrix. So dn over 2 is a diagonal matrix that looks like this: 1 omega 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 to the power n over 2, right? So this is the reason why the Fourier transform can be sped up from n square operations to n log n operations, is because we can define it recursively and then do the speed up of the Fourier transform. Now, as I mentioned earlier, that the applications of the Fourier transform are many, but let me just, applications are in one is signal processing. So if you have a complex signal, then you can sample it and then apply the discrete Fourier transform to it. And then you can work in what is known as the frequency domain and manipulate it, and then get the idea of what the frequency components of those the complex signal is. So signal processing is one application. The other application is polynomial multiplication. And this is based on the fact that, again, based on the fact that the fast Fourier transform requires n log n operations. But the idea is that the convolution, so this is based on the idea of convolution, and the fact that convolution in the Fourier domain is just pointwise multiplication. So that idea leads to faster polynomial multiplication. And in fact, it leads to just the regular, base 10 multiplication. We can do it much faster using this. So these are a couple of applications of Fourier transform. There are other applications in image processing and other areas. Now, it turns out that the quantum version of the Fourier transform, so quantum Fourier transform, takes order of log n square operations, right? Where the number of qubits is related to n as, so little n is equal to 2 to the power n, where n is number of qubits, input qubits, right? So if I compare order of log n square, so this is the quantum version versus classically order of n log n, then this is an exponential speed up. And one of the great applications of the quantum Fourier transform is the Shor's factoring algorithm. And the Shor's factoring algorithm leads to a polynomial time factoring algorithm. And that is one of the crowning achievements of quantum computing. So in the next few videos, we'll talk about the details of the quantum Fourier transform, its circuit implementation, and then how it can be used to speed up the factoring algorithm.